And welcome everybody to the second half of chapter 9, or the second third, as this will take 3 videos to cover all of it. But we're going to cover Norton's theorem, and we often talk about Thevenin and Norton in very short order to one another because they are interchangeable, and you'll see what I mean by that when we get done. So in other words, if you know the Thevenin of a circuit, then you also know the Norton if you do a simple calculation. So we are going to go over the steps to once again deal with these series parallel circuits that are a little bit more complex. That if we did have a very complex circuit, we don't want to have to make a lot of different calculations trying to see how different loads would respond. And so this is an easy way to swap out 4, 5, 10 different loads with a very simple circuit as opposed to changing it out in a very complex circuit. So we essentially look at the performance characteristics between the terminals of A and B where the load resistor will be placed, and then we can either set up a Thevenin equivalent circuit or a Norton equivalent circuit and easily solve those. So here's the first step, and you've seen it before because it's exactly the same as it is in the Thevenin version. Okay, so we find RTH, or if you like, we could say that we're finding RN. Okay, and so this is something that a book will do, I believe, and so it's the same thing. So if you know the Thevenin resistance, you also know the Norton resistance because it's identical. Okay. And just to refresh, you short all voltage sources, you open all current sources, and essentially it's as if you are putting an ohmmeter in between those two terminals. And we use series parallel reduction techniques from chapter 7 to accomplish this. So it's identical to the Thevenin resistance calculation, which is how these two things are related to one another. So the next step here, whereas before we went to find the open circuit voltage at those terminals, now we want to find the short circuit current between those terminals, between terminals A and B. So we're still going to use chapter 7 techniques, or I presume you could use mesh or nodal if you'd like as well, because almost anything, well, essentially anything you can do with chapter 7 you can do with chapter 8. So if you'd like to do mesh or nodal instead, by all means, but essentially we're still building off of chapter 7 techniques. Okay. So in this case, instead of us putting a voltmeter with a very high resistance across the terminals in between terminals A and B, we are putting an ammeter in between terminals A and B, which, as you know, is essentially a short, right? It's less than 10 ohms. If you look at the resistance across the terminals in multisim, it's even less than that, and you can, as you know, you can make that resistance whatever you want in multisim to simulate a real life ammeter. So anyway. So remove the load resistor, find the short circuit current between. Okay, so it's just putting a piece of wire there and then finding that particular branch current. Once you have that current through that branch, then you can draw what's called the Norton equivalent circuit. And this is your Norton current in parallel with your Norton resistance, or again, it's also your Thevenin resistance. So you put the load resistor between A and B, and essentially you can set up a nodal analysis. The only thing is you already know what the current coming into that node is. So it comes in as IN, and it gets split up through the RN branch and the load resistance branch. So there's only 2 branches. So you still need to do a series parallel calculation at the end, when you're swapping the loads out, but then you can go straight into your current division because you already know what the total current coming into this node is here. Okay, so that's the goal, and now we are going to switch over to the board, and we're going to do a few of these problems. And here we go, using a couple of standard value resistors on here. Got a 1.2K, 4.7K, 2.2K, 6.8K. It doesn't really matter. This is a similar problem to what we've done for chapter 7, 8, and the first part of chapter 9 here. So it's the same series parallel combination network. So first thing I'm going to do, if I assume that this is my load resistor, so I'm going to say RL equals 6.8. Okay, sometimes I'll just have an RL here. right? And I don't even tell you what it's supposed to be. Okay, so this is going to be our load resistor, so I take it out, label my terminals. Okay, it's a 9-volt source, so I'm going to short this out, and then, as if I had an ohm meter between terminals A and B, figure out what this total resistance is. Okay? So I can see that this branch over here is in parallel with this branch, so that's a series parallel combination, and then when I add that to 2.2, I'll have the total. So the Thevenin resistance here is 2.2K, because it's in series with the ohm meter here, right, on this side, and then these two are in parallel, so this will be an essentially series circuit once we do this parallel combination. So plus the parallel combination of 1.2K and 4.7K. So I need to do this calculation and write it down so I can add it to 2.2. So 1 divided by 1.2 plus 1 divided by 4.7. Take the whole thing to the negative 1. I get 955 ohms. Just straight ohms. Okay, so that's going to be 2200 plus 955, and that gives me 3.16. It's actually 3.155. I might carry that through K ohms just to get it more accurate. 3.155 K ohms, because it's right in the middle. Okay, let me get this erased. Okay, and so now we're going to rewrite the original, and I'll just do it up here. So we have half of it already. And so this was 9 volts, and now we're going to get rid of this, and we're going to put a short in here, but we're putting an ammeter in, okay, to be clear, because we want to know what this branch current is. So, I'm just going to use Chapter 7 techniques because it's only, I guess I could use nodal analysis, but I'm going to go ahead and use Chapter 7 techniques. So, if I want to find the total current for this circuit, and remember, this is not what we were just looking at. That's something that we do to find the Thevenin or the Norton resistance. What I'm doing now is a typical Chapter 7 problem, so now I'm going to start using the terminology total resistance. Okay, because I want to know the total resistance of this circuit that I have drawn. I realize the load resistor is not in there, but we're trying to find what that short circuit current would be. Okay, so I have now resistance total is 1.2K plus these two, because they're now in parallel. So plus 4.7K in parallel with 2.2K. So I need to keep this calculation. So 1 divided by 4.7K plus 1 divided by 2.2K. Take it to the negative 1. I'm going to round that one up. 1.50K. And this is 1.2K. So that gives me a total of 2.7 kiloohms. Now I can find the total current out of the source and through that 1.2K. I don't really care what this is. The only reason I have to find it is because I need it to do my current division here. And I don't even really care what this one is. I'm only going to solve for this one branch current. So IT is 9 volts divided by the 2.7K ohms. So 9 divided by 2.7, 3.33 milliamps. And so now I know that breaks up into these two currents here. I just want to know what the current is through the 2.2K. And so that's going to be the current coming in. Those two in parallel were 1.5K, so times, this is current division, times 1.5K ohms over 2.2K. So because this is the smaller resistor, I expect this to be about twice as much as this one. 3.23 times 1.5 divided by 2.2 because the k's cancel. 2.27. So 2.27 milliamps. Okay, now I am ready to draw my Norton equivalent circuit. And the Norton equivalent circuit, when I ask for this, is going to be unloaded. There is no load there. It's just available to accept a load resistor. So that's why we label it like with the terminals A and B. So you can plug your load resistor value in as many of them as you want. So this is 2.27 milliamps. This is 3.155 kilo-ohms. And so that would be my answer for my Norton equivalent circuit. Now earlier I said if you know the Norton or the Thevenin, you can calculate the other. And here's the relationship. So V equals I times R. In our equation, the Thevenin voltage is equal to the Norton current times RTH. Or you could also write it that way. Either way is correct because RTH equals RTN. So if I ask you for both the Norton and the Thevenin equivalent, all you're doing is a simple calculation. So to find the Thevenin equivalent here, I've already got half of it because this is just 3.155K. And so now I need to find this voltage by taking 2.27 milliamps of current times the 3.155 kilo-ohms. And the K and the M will cancel, so 2.27 times 3.155. And I get 7.16 volts. Okay? So if we were to have an open, instead of an A here, if we had a voltmeter, remember this one is very, very high, it would have been like taking 4.7K over these two added together times 9 volts, and that would have been our voltage out. So that looks to be correct. Okay, so there's my Thevenin equivalent. I'm going to solve this now using the Norton equivalent circuit though. So you can see, work with the current source. So we said our load resistor was 6.8K. So I always want to know two things about the load. I want to know what the voltage on the load is, and I want to know what the current through the load is. Okay? So we'll do the current first. So the current through the load is the current through the 6.8K. And so that's going to be a 2.27 milliamp current coming in. I guess we should do these in parallel real quick. So the equivalent of 3.155K in parallel with 6.8K, 1 divided by 3.155 plus 1 divided by 6.8. Take the whole thing to the -1, and I get 2.16 kilo-ohms. So this is going to be 2.16 kilo-ohms over 6.8K. So 2.16 divided by 6.8. And times 2.27. And I get 719 micro. Which makes sense because this is half the size as this, and so I would expect this to take the majority of, this to take the majority of the current, and this one not to, because this one has twice the resistance. So 719 micro. So then to find the load, I'm just going to use V equals I times R. So 719 microamps times 6.8 kilo-ohms. 4.89 volts. Okay, so let's consult multisim and see how we did. Okay, and so now I'm just going to put an ammeter in here because this is our original circuit, and we should be expecting, what did we say, 719 microamps. So let's see what happens. There's 720. I'm happy with that. And we also had a voltage drop across the load of 4.89 volts. So let's try that out. Add a voltmeter here. I could always just put a node voltage probe in there because it's referenced to 0 down here on the other side of this load resistor. But I'm just going to put a multimeter in, just to make it easy. And there we've got essentially 4.90, right? So it's rounded up just a touch, but I think that's exactly the same. Okay, so now what I want to do is put in, so the current was, the Norton current is 2.27 milli. This was 3.155 kiloohms, and the load resistance was 6.8 kiloohms. So I want to know what the current is through that, and I want to know what the voltage is here because it should be identical to what we ran up here. And there we go, 4.89 and 719 microamps. Okay, so looks like we did it correct. Okay, so now we're going to do one that's a little bit different, and really it's not that different because I'm just sort of rearranging where the load resistor is. Okay, I'm so used to seeing things over on the right side. I'm going to show you that it doesn't matter if the load resistance is here or anywhere. Okay, as long as you use your Chapter 7 techniques. So in this case, the first thing we're going to do is find RTH or RN. I always call it RTH. Probably because I like Thevenin better, but I like Norton too. I don't really have a preference one way or the other, but I've always just written it as RTH. So anyway, to do that, I had to take the load resistor out. We haven't even talked about what the load resistance is yet, but I'm going to go ahead and scrub that. Now here's the terminals. This is B, and this one will be A. I'm going to short the 25 volt source. And show that it's been shorted here. Okay. So now I have a similar situation to what we did in the Wheatstone bridge, trying to find the total resistance between those two terminals, right? So in this case, I know that I've got these two in parallel, and I know I've got these two in series with one another. Okay, and so I can kind of do what I did before, where I'm gonna go ahead and do this branch in parallel with this branch first, and then rewrite it. Okay, so this first one here, I know that's what we're trying to find. We're trying to find RTH right now. So the first thing I'm going to do is find the REQ of this branch in parallel with this branch. So that's 1 divided by 100 plus 1 divided by 600 on this branch. So the -1. And we've got 85.7. Just ohms, just regular ohms. So now I've got this equivalent, A and B, and this equivalent, and because of where my A and B are, you might be able to see, if I add those together, it's 1.5K, that essentially those are in parallel with each other, okay? And if you just flip it on its side and put the terminals on the outside so that it looks like this, it becomes a little bit more obvious, right? 85.7 ohms and 1.5 kiloohms. Remember, if you have branches in parallel, you can rearrange them typically however you want in terms of doing your calculations. Okay, so to find the RTH here, I'm taking 85.7 in parallel with 1.5K. 1 divided by 85.7 plus 1 divided by 1.5k. Take the whole thing to the negative 1, and we get 81.1 ohms. Remember, it has to be smaller than the smallest value, which is 85.7. Okay? Alright, so 81.1 ohms. Now, I'm going to come back up here. And this is going to be interesting. Okay. So I need to put the source back in, get rid of A and B. And remember what I do here. I'm putting a short in by essentially putting an ammeter. This is something you should never do, by the way, in real life, right? Because you will damage the meter, because somewhere you're shorting something out. Okay? So what you're doing, and remember, you can look at this as if it were just a short. Right? We know that the ammeter has, what, less than 10 ohms? So, you know, it's essentially a piece of wire at that point. That means that when the current comes out of the source and comes into this node, you'll notice, let me make this in a different color so you see the contrast. Let's do orange. So this is all one node. But see, you can't stop it there. It's this. Do you see how that extends all the way down to here and to the negative side of this terminal? That is a short, which means it's going to bypass this branch in parallel and this branch in parallel, and the only resistor in this circuit, the way I have it drawn, is the 100 ohm. So this is a 25 volt source. So my Norton current here is just the current through the 100 ohm resistor. So 25 volts divided by 100 ohms, and it's what? That's 2.25, or the hundreds always give me a problem. 250. 250 milliamps. Okay, so there we go. So now I have my Norton equivalent. What they do with my orange cap. Alright, so now we want to redraw the circuit. So that worked out nicely. And so now we've got, what did we say, 250 milli. And that comes into a branch with 81.1. And let's make the load 250 ohms. Okay? So now we've got one with, in parallel here, 250 ohms. So remember, the first calculation you should really do here is to find this parallel combination. So 1 divided by 81.1 plus 1 divided by 250. Take the whole thing to the negative 1, and I get 61.2 ohms, just regular ohms. Okay? So that means the current through the load is going to be 250 milliamps, and I expect this one to be smaller current than this, so it's going to be less than 125 milli for sure. And so 61.1 or 61.2 ohms divided by 250. 61.2 divided by 251, and I get 61.0. I'm going to round that. Milliamps. And so then for the load, I'm going to take the 61 milliamps times the 250 ohms to find the voltage drop. And 15.3 volts. So 15.3 volts and 61 milliamps. So let's consult Multisim and see how we did. Okay, so here we go. We've got Multisim as soon as we switch it over here. And we're going to see how we did. So here's the original circuit, and here's my load resistor right here. So really I just need a voltage probe here because it's referenced to 0 already. So the node voltage is always referenced to 0, so this can serve as the voltmeter measurement here. You could always grab a DMM over here and put it around if you wanted to. But then I also want to know what that current is on that branch. Okay, so those are the two things I want to know from up here. Those two things should be identical to what I measure down here. Again, I'm going to use a voltage probe because it's referenced to 0 already on the other side. And I'm also going to pull down a magic ammeter probe. And these two sets of measurements should be identical if we've done it correctly. And looks like they agree. Okay. All right, well, thank you very much for watching this video. And there will be a third part to Chapter 9 where we cover superposition and max power transfer. So look for that. Thanks.